Okay, in this video we're going to look at, it's an introduction to matrices, so we're going to kind of give a definition of what a matrix is. We'll do some matrix operations, we'll do addition, subtraction, scalar multiplication, and also multiplication of matrices, and talk about a couple of other things. So what a matrix is it's a rectangular array of numbers that are usually named by the capital letters A, B, and C, etc. Each entry in a matrix is referred to A, Ij, or Bij, or Cij, depending on if we're naming the matrix A, B, or C, such that I represents the row that entry is from, and J represents the column that entry is from. And how matrix dimension is defined is it's the number of rows by columns. So we refer to a matrix as an M by N matrix, indicating a matrix of M rows and N columns. Okay, so we're going to go ahead and identify the dimension, and also get kind of familiar with the definition of the location of the different entries in the matrix here. So this is continuing on the Chapter 7 notes. So if I have the matrix X and Y, there are 2 rows and 1 column. So this is a 2 by 1 matrix. So first row, first column is X. Second row and first column is going to be Y. Okay, and then we'll mention that that matrix XY is also a column matrix because it consists of 1 column. Now, some books will use, and I think your guys' book will use the kind of the square brackets. There's no difference between the bracket and the square, the bracket or the kind of parentheses notation, so you can use whatever one you want. I tend to use the parentheses notation for the matrix. Okay, so how about 3, 2, -1, and 5 as a matrix? There are 2 rows and 2 columns. A11 is 3. A12, so first row, second column is 2. And A21, so second row, first column, -1. And then second row, second column is going to be 5. And notice that the rows and the columns are the same for number 15, so we call that a square matrix. Okay. And then we'll go back and mention that number 14, we can call that a column matrix. Sometimes it might be referred to as a column vector. All right, number 16 is 23 and -9. So there are, that is not correct. Sorry. There is 1 row and 2 columns. So I have that in error. Let's see. So first row and first column is going to be 23. And first row, second column is going to be -9. And so this might be referred to as a row matrix or possibly a row vector. Okay, let's do one more. We'll identify the dimension and then also list all the entries in the matrix. So this one's going to be a little bit larger. So 170 minus 2, 4, -8, 1, 5, and 2. So this has 3 rows and 3 columns, so it's referred to as a 3 by 3 matrix. It is also a square matrix because the rows and the columns are exactly the same. And first row, first column is 1. First row, second column is 7. First row, third column, 0. Second row, first column, -2. Second row, second column, 4. Second row, third column, -8. Third row, first column, 1. Third row, second column is a 5. And third row, third column is a 2. So there's all the parts there. We define what the dimension of this matrix is. Okay. So now we kind of have a familiarity of the entries of the matrix and also dimensions. We're going to go ahead and define what it means to do the addition, subtraction, and scalar multiplication of matrices. So we'll go ahead and speed that up. So matrix addition and subtraction. If we want to add or subtract 2 matrices of the same dimension, add or subtract the corresponding parts. The resulting matrix C will have the same dimension. If A and B have different dimensions, then that should say A plus minus. It kind of looks like it's an equal sign, so whether we're adding or subtracting the two matrices, if they don't have the same dimension, that's undefined. For scalar multiplication, so scalar refers to a scalar in a field, and so for us, we'll just assume that means that's the real number, so any real number. So any size matrix can be multiplied by a number, or scalar. Simply multiply each entry by whatever the scalar is. So we'll do an example of that, and we'll do some examples of adding and subtracting matrices. We'll get into matrix multiplication a little bit. Okay, so here are all our matrices. Oops, we don't want to say that, and that's like the Matrix movies. It's pronounced matrices. So we have A is a square matrix, 1, 2, 3, 4. Matrix B is also a square matrix, both of them being a 2 by 2, 5, -7, 11, 12. C is also a square matrix of 2 by 2, -1, -2, -3, and -4. Matrix D is a 3 by 3 square matrix, and entries are 7, 3, 1, 0, 1, -3, 4, 9, and 1. And we're going to do some operations. So we're going to find A plus B. They're both 2 by 2 matrices, so we can go ahead and add them. And so we're going to add the corresponding parts. Okay, so 1 plus 5 is 6. 2 plus -7 is -5. 3 plus 11 is 14. And 4 plus 12 is 16. Now we're going to add 8 matrix A and C. Okay, and what's going to happen is it's 1 plus -1 is 0, 3 plus -3 is 0, 2 plus -2 is 0, and 4 plus -4 is 0. This is the 0 matrix for 2 by 2s. And it may also be called the additive identity for matrix addition. And the additive identity, for example, for numbers is 0. So if I take a number like 5, and 5 plus a 0 is going to be the same thing as 0 plus 5, which is 5. So it doesn't change whatever you're adding. Whatever you add 0 to doesn't change it. And same thing with the 0 matrix. Okay, I think we're going to do 2 more of this type. So we're going to go ahead and write down all those matrices again. Okay, so 3b minus 2c means we're going to multiply 3 times matrix B, and then subtract from it 2 times matrix C. Okay, and so kind of is like the distributive property, so we're just going to multiply that 3 through. So 3 times 5 is 15. 3 times -7 is -21. 3 times 11 is 33. 3 times 12 is 36. What I like to do here is I like to go ahead and multiply the -2 through. That way I'm not subtracting negatives later on, so it helps me avoid mistakes here. So we're going to treat it as multiplying the -2 through, and so then we'll have addition of the 2 matrices when we're all done. So plus, distribute that -2, so we got 2, 4, 6, and 8. And then we can go ahead and add the 2 matrices together. 17, -17, 39, and 44. Okay, and the last one of this matrix addition, subtraction, and scalar multiplication, we're going to look at adding matrix C and matrix D, and they are not the same dimensions. C is a 2 by 2 and D is a 3 by 3. So that addition is undefined, and that's it. We just say it's undefined and we move on. So we're going ahead and mentioning what their dimensions are, and that's it. Okay, so matrix multiplication is a little bit trickier. It does not work how you would expect. So you do not multiply corresponding parts. What you're going to do with matrix multiplication is you're going to multiply a row of the first matrix by the column of the second matrix. So you do 15 times 2 and -21 times 6. And we'll get through it and we'll do a bunch of examples of that. So let's go ahead and define matrix multiplication. So to multiply 2 matrices A and B, the columns of A must be the same or must match the rows of B. Otherwise, the multiplication is undefined. if AB is defined, the resulting matrix will have the same number of rows as A and the same number of columns as B. Okay, so we're going to be given a bunch of matrices to play with. Okay, so A is 2 by 2, B is a 2 by 2, C is a 2 by 1, D is a 2 by 2, E is a 3 by 3, and letter F is a what do we got here? 3 by 1. Okay. All right. So let's go ahead and try out multiplying A by A and B together. So matrix A, matrix B. They're both 2 by 2, so we're going to go ahead and mention their dimensions. So 2 by 2 and 2 by 2. Columns must match rows, so columns of the first match the rows of the second, so that looks good to us. So this multiplication is defined. The exterior, by exterior I mean the rows of A and the columns of B, that's going to determine the dimensions of our product, which is a 2 by 2. And then what I like to do is I like to write down the locations of everything. So we have row 1, column 1. So that tells us exactly what we need to do. So we're going to multiply the first row of the first matrix by the first column of the second matrix. So we're going to take 1 and negative 1 times 0.5 and negative 0.5. So we're going to multiply 1 and 0.5 and get 0.5. And then we're going to multiply negative 1 times negative 0.5, and that will be plus 0.5. Okay? Then we're going to do row 1 of the first matrix times column 2 of the second matrix. Okay, so we're going to do 1 minus 1 times 0.5 and 0.5. So 1 times 0.5 is 0.5. And negative 1 times 0.5 is negative 0.5. Okay. Now we're going to do row 2, column 1. So we'll multiply the second row of the first matrix times the first column of the second matrix. So 1, 1 times 0.5, 0.5. 1 times 0.5 is 0.5. And then 1 times negative 0.5 is negative 0.5. And finally, row 2, column 2. So row 2 times column 2. 1 times 0.5 is 0.5, plus 1 times 0.5 is 0.5. And then we'll go ahead and simplify that down. Okay, and that is also the 1001, that's the identity matrix for 2 by 2. So sometimes it is called this, or some books might use I2. And what the identity matrix looks like, how it works is it kind of works like 1 for numbers. So if I take like 5 and I multiply it by 1, that's the same thing as 1 times 5, which is 5. So it's called the multiplicative identity, and it doesn't change the matrix if we multiply by the identity. So we'll be interested in that in the next. I think it's the last section we're going to be looking at when we're doing the inverse matrix method, and we'll be really interested in the identity and inverses and that kind of stuff. Okay, what do we got? We got a couple more to run through here. So let's see, we're on number 23. Okay, so we're going to be writing the same stuff as we did before, so we'll go ahead and speed that up. And one comment or something I'll mention here is it appears that the negative here got lost in copying that over. It's okay. We can leave it as a positive 5 there. It's not going to hurt anything. Okay. For our examples, we're going to multiply matrix D and C together and see what the dimensions are and if this multiplication is valid. So D is the identity for 2 by 2s, and that's a 2 by 2, and matrix C is 2 and 6. So that's a 2 by 1. The columns of D is 2, and the rows of C is 2. So we do have a match. So this is a valid multiplication, so we can go ahead and multiply those. Okay, and the exterior is the rows of D is 2 and the columns of C is 1, so this is going to be a 2 by 1 matrix. Okay, and so that's going to have 2 rows, 1 column. So that kind of helps us tells us what to do. So row 1 times column 1. Okay, so 2 times 1 is 2, 0 times 6 is 0, and then row 2, column 1. So 0, 1 times 2, 6, 0 times 2 is 0, and then 1 times 6 is 6, and then we'll go ahead and simplify that down to 2 and 6. One thing we'll go ahead and mention since we're here, D times C would be 2, 6, and that's a 2 by 1 matrix, and matrix D, 1, 0, 0, 1, that is a 2 by 2, and if we check columns and rows, this is a no match. Okay, so that is undefined. Okay, and so that tells us that DC is not equal to CD. So that's not true because one of them is not even valid. It's not a defined operation there. And so that's one of the things about matrix multiplication, and it's not commutative. So, for example, something that is commutative is regular multiplication of numbers, because 3 times 2 is equal to 2 times 3. So, matrix multiplication not necessarily commutative. Okay, let's see. We got about 3 or 4 more examples. Let's keep going. All right, and we're going to have the same matrices again. This time we're going to look at multiplying AD. Okay, so A is the 1, minus 1, 1, 1, and that's a 2 by 2, and matrix D is 1, 0, 0, 1. That's a 2 by 2, and columns match rows, so this multiplication is defined, and the exteriors are 2 and 2, so this is a 2 by 2 matrix as a product. Okay, so it's going to have a row 1, column 1, row 1, column 1. 1 times 1 is 1, minus 1 times 0, 0. And then a row 1, column 2, row 1, column 2. 1 times 0 is 0, negative 1 times 1 is negative 1. Row 2, column 1, row 2, column 1. 1 times 1 is 1, 1 times 0 is 0. Okay, and then finally row 2, column 2, row 2, column 2. 1 times 0 is 0, 1 times 1 is 1. We'll go ahead and simplify that. 1 minus 1, 1, 1. And that is exactly A. That is exactly A. And 1, 0, 0, 1, that's the identity matrix. So which one is that? That's matrix D in this case. That is the identity matrix for 2 by 2 matrices. And you see that when we multiplied A by the identity, it didn't change anything. So that's good. That's what we want with the identity matrix. Okay. You can also multiply AD, and that will also give us A there. So you can try that on your own. It'll work out. If we're the D didn't come there. Okay. So if you're multiplying by the identity 2 by 2 and you're using a 2 by 2 matrix, that'll work out fine. Whereas if we were in like problem 23 there, the matrix 2, 6 was a 2 by 1, so it wasn't the same dimension. So we did have one valid multiplication, but we didn't have 2 valid multiplications. We couldn't commute there, but you could commute with the square matrices, and as long as one was is the identity there. Okay, what do we got? A couple more. So here's it all again. So we're looking at 25 here. So we're going to multiply matrix B and C. So matrix B is all the 0.5s, one of them being a negative 0.5 in row 2, column 1. And matrix C, which is 2, 6. Okay, so we do have a match. And this is going to be a 2 by 1 matrix. Row 1, column 1, row 1, column 1. So that's going to be half a 2 and half a 6. So that'll be 1 plus 3. Then row 2, column 1, row 2, column 1. Negative half of 2 and half of 6. Negative 1 plus 3. And that simplifies down to 4 and 2. And that's it. Okay. All right, what do we got in this one? Okay, in this one we are going to find F times E. Okay, so F is a 3 by 1 column matrix. and matrix E is a 3 by 3 matrix. So we check the columns and the rows, no match, and this is undefined. That's it. We just say it's undefined, move on. So FE is undefined. What about EF? Could we do EF? Let's try it out. So we're going to look at E times F. Matrix E is a 3 by 3 matrix. So we'll go ahead and write that down. Matrix F is a 3 by 1, excuse me. Okay, and so columns match rows, so this is good. So this matrix multiplication is defined, and so we're going to have a 3 by 1 matrix. So we'll do row 1 times column 1, so row 1, column 1, so 1 times 1 is 1, 0 times 3 is 0, and 7 times 2 is 14. Okay. And then we're going to do row 2, column 1, row 2, column 1. Negative 1 times 1 is negative 1. 3 times 3 is 9. 0 times 2 is 0. Row 3, column 1. Row 3 is 0, 5, 6. And column 1, 1, 3, 2. 0 times 1 is 0. 5 times 3 is 15. And 6 times 2 is 12. And then we'll go ahead and simplify that down. Okay, and we'll go ahead and mention that FE is not equal to E. Well, I meant to say, not equal to EF. Pardon me. So FE was not even defined, but EF was defined, and we could find the multiplication. So another instance that matrix multiplication is not commutative. Okay, we'll end with a little bit of word about the identity. And we'll do more with the identity in the last section, which I think is 7.7. Okay, so I1 is a 1 by 1 matrix, so it's just 1. I2 by 2 is sometimes called I2. And so we have a diagonal of 1s, and then everything else is 0. Sometimes this is called the main diagonal. I3 is a 3 by 3 matrix, and then you have 1s along the main diagonal and then 0s everywhere else. And then I4 is a 4 by 4 matrix, and then it'll have a main diagonal of 1s again. Okay. And you can keep going and imagine an n by n identity matrix. And we're going to be getting into something called Gaussian elimination. And we'll want all of these to be zeros down here. Whoops. All of these to be zeros here. And we'll go through a process for getting that lower triangle to be zeros there. Last thing I'm going to mention here is if I take the n by n identity matrix and multiply it by a matrix of dimensions n by m, the columns match the rows, so we'll get that matrix A back. Okay, or if we take an n by n matrix and multiply it by the identity m by m, that's going to give us back that matrix n by m. Okay, and then for square matrices, if you take matrix A, which is a square matrix, and multiply it by the appropriate square matrix, square identity I here, that'll be the same thing as IA, which is equal to matrix A there. Okay, so that is it for this video. A little bit of matrix operations, getting familiar with them. So we will see you next time.